Yo, it's your boy. It's just your boy. What's up, guys? I'm back a few minutes later in the same shirt with more problems from modern electrodynamics written by Zhang. Um, this time we're going to finish up the problems that I highlighted for chapter 2. There are plenty more. I think I've done most of them. Like most of the important ones that are like, this is definitely something that people should know if they're getting in, or they're doing problems. Anyway, let's just hop into it, and then I might do a couple of them from chapter 3. So Zhang will ask us in one problem from chapter 2. I don't give numbers because I think that's a copyright infringement. So I'm just going to say the guy's name. He asks us to do specific tasks as if we're his slaves. Zhang will ask us to find the dot product, or find the divergence of this beautiful function called E. And E is the electric field. The electric field vector. And the definition of this very lovely and very mathematically elegant expression is 1 over 4 is the divergence, or del dot 1 over 4 pi, the integral of some volume B. Anyway, the song is West African Tunes by Bully Mix. Some more Bully Mix. Just a switch, really, of this function rho of various primes with this difference of position vectors. Now, a bit of explanation on the definition of things. This, wow, it's too far. Anyway, it's going to be too far for a minute. I apologize. Yeah, it's going to be a little, I can turn it a little bit. No, that doesn't help. Alright, oh well, sorry. So a little bit of explanation. This expression here is the position vector R minus some position vector primed, which in Zhang and Griffith's electrodynamics indicates the position of some charge, some infinitesimal charge, which is coming from this sucker here, this density, and it's integrated over this R prime here, which that's part of the volume, a volume element of the charge density. So we get the position of the charge minus the position of evaluation over the magnitude of the difference. The magnitude of the difference cubed. Zhang just goes ahead and does it the way that I like it. I like to see it this way, as opposed to dealing with unit vectors in some curly bracket. Whatchamajigger. Now this would also be a curly bracket. Squared. Yeah, I think that this is a lot more not more helpful than this is. They mean the same thing. You're just defining curly brackets as the difference of vectors, or curly R, scripted R. I've heard a bunch of different names for that thing. Anyway, so we're looking for the divergence of this sucker. Well, the divergence is a vector operation, just like dot product. That means it's only going to interact with other vectors, and the only other vector that we've got in this sucker is that. There you go, right there. Right there, I introduced it. These are vectors, by the way. I don't put the vector sign under del because I know what it is. I'm writing it for me and for you, but I'm explaining it to you that it's a vector. It's a vector operation. So, taking the hint from Zhang that he gives us in chapter 2. This expression. So I'm not going to write all this nonsense out. More or less, the important part is just indicating what del is acting on. And in this case, it's on the scripted R part. And what is this? What does this expression come out to? Well, again, the hint from Zangwill was that we write this expression as the del of right. Right. Is that it? I think it is. Yes, of course it is. Boom. All right. So, all right. So this is the hint that Zangwill gave us, that this vector here is just the gradient of this magnitude. That means this is the Laplacian of this magnitude. I'm telling you, sometimes, I forget relationships. That's why it's very helpful to write down all of your problems. Usually it takes me hours to do homework, or used to take me hours to do homework. I'm not doing homework anymore right now, except for you all. Because I would write down all my answers in books like these, and then I would then have to transcribe these answers onto another sheet of paper. So it gave me twice the amount of practice that I gave my peers most times. In a lot of instances, that's how I sold. I was able to sell notes and things. I don't typically take notes in class unless it's a subject that I hadn't read up on the night before. But I was able to sell notes because I had all the problems, and I had done the problems twice. It just gave me a bit of a leg up. So this expression is what? Well, Zangwill gives us to it as 4 pi direct delta r minus r prime. You can go to Griffith's electrodynamics, and you'll be able to get a formal expression or formal explanation on why this is the case. The nuts and bolts explanation is just that the nuts and bolts explanation is, this function dies down really quickly. You know what a 1 over r squared type of function does. So the divergence of it is okay, so let me just draw it. This is r. This is f of r. Well, let's do f of scripted r. Well, we'll do f of r for now. Technically this is f of scripted r. It's because the Kronecker delta is the difference between where this function is 0 or where the charge is in this case, and where we're evaluating. So if we look at it from the perspective of r, and then we take the function of scripted r, well, if this is r prime, then what does the function do? The function is infinite here, and then goes to 0 as r increases, and it goes relatively quickly, both sides. So the divergence is basically the mean value of the function, and the mean value of the function more or less is in this area, right? Well, it's a direct delta, and the closer you get to r prime is the closer and closer you get to an infinite peak, or the peak of this function, which is infinity, and that's how you're getting a direct delta by a factor of 4 pi, and that comes from integration. And it comes from integration. And I also think it might come from the fact that we're dealing in spherical coordinates. This may be written in one-dimensional, but this is a function of r, so that's 3 separate directions I'm taking into account at one time. So yeah, that's where the 4 pi comes from. Next, Zangwill asks us to find the curl of this very beautiful function, with very beautiful vector function e. So we can again skip all this nonsense and say the curl of e. I'm skipping all this nonsense, so I'm not rewriting it in the final answer, because if you know what a direct delta function is, it takes where the function r is, it pinpoints, as I'd said in the last video, is that it pinpoints where the direct delta function is going to be 0, and it just, sets everything to that point. This r prime is just going to become an r. This function here, this charge density is just going to become an r, and we're integrating over that particular volume wherever the charge is. Okay, yeah. So the direct delta, the direct delta is just indicating where the function is, and we're integrating over the size of the volume. God damn it! I'm gonna get better at it. I'm gonna get better at explaining this nonsense. But basically that's what it's saying. Just saying we're integrating over this volume, and the cross here is more or less cross of del with this function here. And if you remember your vector relationships, position vectors are irrotational, so this is going to be 0 by definition. Yeah. By saying that position vectors are irrotational, is just saying that if you have position vector, there's no bend here. It's not going around. It's this vector here and here are indicating where something is. There's no rotation about a point or any of that nonsense. Formally, if you do the arithmetic, and you expand this out the way that you're supposed to, not only are the position vectors irrotational, but you also have a gradient, which is irrotational. Because if you remember what this vector relation is with respect to a magnitude that we just did, del cross del, that's 0. So far, so easy. Somewhat difficult to explain, but so far so easy. My boy Zhang Will then asks us to evaluate the divergence of a B field. And what does a B field look like? Well, B field looks like this. Is it 1 over mu? That's a good question. I think it's 4 pi over mu naught, or mu naught over 4. I mean mu naught over 4 pi. I'm sorry, people. I had not had my coffee this morning, actually, believe it or not. And then we got this vector called J. And we're crossing it with our beautiful position, or curly R. For now, let's do curly R because it's already, you guys can't see, and I might as well save some time. So our curly R vector. Do that curly R. What is that? Curly R. There we go. So this vector here is called the current density. Current is directed. Alright, let's do it. Easier said than done, Robert. Well, we did a problem like this back in chapter 1. We're going to drop all this nonsense again. We did a problem like this back in chapter 1, and we know that it's 0. And why do we know that it's 0? Because what does it come out to? What does it evaluate to? This evaluation is curly R dot J prime crossed curly R. Actually, it's really curly R. There you go. We did this in chapter 1. I just looked at the problem. I realized that we had done this because we took a derivative of a function that had some vector a with cross the position vector, and this is a position vector. It's a particular position vector, but there you go. That's it. That's all it is to it. It's 0. Curly R dotted with what's already crossed with itself is going to be 0. So no more work needs to be done. And I don't feel like actually writing out the components and doing the Kronecker deltas and things like that for that problem anyway. Did it in my notes, but I don't feel like doing it here. Just being honest, man. Just being honest. So then he asks us to take the cross product between the B vector, which he gives us this hint that it's also helpful to use the it's helpful in the continuity equation, the continuity of charge, which I'll go into a little bit later because I have a problem on that anyway. And this more or less comes down to the cross between J cross the difference vector. Yeah. I might start writing down curly R, even though I don't like curly R. I might start writing it down. Because Robert needs a break. Well, what is this? Back cab rule. Back cab. Del dot curly R. Back. AC. Yeah. Back. Curly R. Here's J. If you don't remember what curly R is the difference vector. Minus cab. Yeah, that looked creepy as fuck. Alright, so divergence of this sucker. It's just 3. Divergence of this sucker, well, this is 0 because we're dealing with a steady state condition. Del is a function of position vector. This is a function of where the charge is located. So that's going to be 0. We don't have to worry about this sucker. But this thing there, that right there, buddy, that right there, that right there, that right there, what is that? I told you what that was. Dirac delta. I'm having too much fun. Dirac delta, so what does this function come down to? 4 pi j function of regular r. Boom! Put that back in the B field and you're finished. There's your cross product. Well, that's what this is, but you also then have to evaluate. You also have to evaluate the Dirac delta with the volume element and blah blah blah, because you're integrating again where the current is flowing. And that's it. That's that problem. Yeah. That's it. Whoop whoop. Alright, so we got one more problem. Actually, we may have a couple more. We're only at the 20-minute mark. So I'll do a couple more. One of these problems, or the next one that I'm going to do, deals with a physical concept. Whoop-de-doop-de. You know what? Don't fuck with what. Don't rule or word from the wise. Don't fuck with what's not wrong. Don't do it. Don't do it. So we get this problem from Zangwill that asks us to prove that, the curl of a B field, it doesn't make sense. It doesn't make sense that how did Zangwill put it? I don't ever write the full problems down in my notebooks. I just solve them. But he's asked us to sort of let's prove that for a time-dependent charge that there's a displacement current for a time-dependent charge. And what is a displacement current? Well, a displacement current is it's really a good question, because I don't really know that well myself. I only know it from a theoretical point, which is pretty shitty, considering the fact that I took the course. I know from a theoretical standpoint that it's kind of a consequence of this B fields having a curl, of the electric again, because electrodynamics is so intertwined with B fields and E fields, and how they're more or less the same thing, except differences of time and a space derivative. This displacement current is just a consequence of the B field being rotated. It's sort of like it's sort of like if you think about how there goes my phone. It's sort of like how you think about a rotating frame of reference. You get these extra forces by the rotation, due to the rotation. You have your Coriolis forces, you have various centripetal forces, fictitious forces like the centrifugal forces. You'll have consequences of just these rotations, and that's the best way of understanding what a displacement current is. So that you have this regular current, which is a physical current, and then you have this consequence of the charge changing with time, that creates a new current, or a variation in the current, which is just this added portion of the B field cross product. And so if we write all this out mathematically, what is the cross of an electrostatic B field? Well, the cross of an electrostatic B field is mu naught J. Sort of in the same sense that the divergence of an electrostatic E field is the charge density. So we have this mu naught J, and how do we go about proving that for a time-dependent charge there needs to be some other consequence of this cross product? Well, the first thing that I thought was, okay, let's take Zangwill's hint and use the conservation of charge equation. And what that is that the divergence of the current is, make sure that I got this right, because I always screw up equations like this. Divergence of the current is the change in the charge density, the time derivative change of the charge density. And for a magnetostatic field, well, this is consistent, because what is the divergence of J? It's 0. We're dealing with a steady state condition. where you have the same amount of charge that's flowing into a space is the same amount of charge that's flowing out. You don't have any magnetic monopoles. You don't have things like raging fluids of magnetic field of current coming in or coming out of a particular volume, i.e. the divergence case is leaving or flowing into, without the same amount flowing out. So for a time independent charge, this is 0. But we're saying that we have a time dependent charge. Therefore, this is unacceptable. We need something else. And that something else we need, we're going to call A. Just going to give it some arbitrary name. I'm going to call it A. And this is going to be the case then, the divergence of this cross relationship here now this can still be 0. Yeah, that can still be 0, right? Yeah. Ooh, well, excuse me. My back. It's my back. Really, it's my back. So this can still be 0. Well, actually, this is 0. It has to be 0. Why does it have to be 0? Because, irrotational cross B field. This irrotational diverted outward, well, it's got to be, if it's rotating, it has to leave and come into, that volume. Well, it has to leave a particular volume, in this case like a three circle, in all directions at the same rate. So this must be 0. And this comes down to mu naught divergence of J, we already said was this, minus rho dt plus divergence of A. Let's move to this side. So mu naught del rho del t equals the divergence of A. Doesn't really help us, because what does this mean? Not much of anything. There's no easy way of getting A by itself so that we can have a simplified expression. But we do know what even a time dependent charge relates to with how it relates with a divergence, in the sense that we have mu naught del t divergence. Well, we have an epsilon naught, actually an epsilon naught factor, divergence of an E field, a time dependent E field. This comes from Gauss's law. And this is also a divergence. We can take the divergence out of this delta t, because t doesn't affect del. Del doesn't affect t. We're not dealing with any relativistic relationship, so we don't really have to worry about that. This isn't quantum electrodynamics. Shut up, Robert. Sounded like some wacky professor. Shut up. Alright, so we don't have to worry about that shit. We've got a mu naught epsilon naught del. Well, actually, you can take del even further out because these are constants. So del mu naught epsilon naught d e vector dt equals del dot a. We have a new relationship for a now. A is that shit. This is actually a 1 over c squared, c being the speed of light. That tells you that the displacement current is radiation. It's background radiation because the charge is changing with respect to time, or in this case, the electric field is changing with respect to time. And A really is something called the displacement current. I don't know the historical reason of why they call it displacement current, but the name isn't really a misnomer, and it doesn't make, it doesn't not make sense. So I think it fits. And it's fit for this long, so fuck it, keep it. So there we go. What was the point of this problem? The point was to show that for a time-dependent charge, we needed an extra term in this relationship. And in this case, we needed the displacement current. This sort of problem, it forces you to like go back and, well, Zangwill does give you the hint that, use the continuity equation to help you. But it forces you to go back and take a step back and like analyze the next, or how to integrate multiple formulas or multiple physical concepts into solving a problem. And I felt like this was a good way of doing it. Sort of Griffithsy in the manner that you had to go about doing it, but it's sufficient for the it's sufficient for where we are in the book. And the problems definitely get harder when you have to integrate multiple concepts, especially if you're dealing with quantum mechanical type approximations, etc. All right, so last problem. Last problem is sort of like a classical mechanics problem and a differential equations problem. I'm not going to say I knew how to do it off the break because that would be a lie, but I will say that once I sat down and thought about the method that I was going to go about solving it, then it was easy. A lot of times when you're dealing with problems like these that focus heavily on just solving a differential equation, you have to just go back into your Rolodex of differential equations. Whether or not you're like me, you have a book full of differential equation solutions that you have, or you look up numerical methods. In this case, you didn't need a numerical method, or you throw it into your Mathematica, your MATLAB solutions, and then just go ahead and do it. All right, so the problem says we have a charge at the origin, we call that O, of charge Q, and then we have a charge at some position D. We'll release it at we have another charge of charge Q, same charge as the origin charge, and we have it at position D, and we're going to release it from D. And what we'd want to do is we want to find the asymptotic relation, or the asymptotic velocity as the position of this particle goes to infinity. And well, okay, that's somewhat of a classical mechanics problem. So if you've done Griffiths, you've seen, you may not have done this exact problem, but you've seen at least what it means for a particle to be, to be repelled to infinity, and what that velocity is, or the terminal velocity. If you've done classical mechanics, which is the terminal velocity is when time goes to infinity. What is the velocity at that point for like a falling object, or in this case a repelled object? This is more or less the same sort of thing. So it's differential equations based as opposed to, you know, um, more like an electrodynamics problem. But I felt like this was a good enough like refresher into differential equations. So where do we start? Well, let's start with Newton's law. We got a force, and that the total force on this particle, because this is the particle that we're speaking in reference to, has a mass m, is, let's not use d, is x double dot, since we're moving in one direction. This is Newton's law, and this is equivalent to what is the force that acting on this sucker? It's only the electrostatic force, which is 1 over 4 pi epsilon naught. Let's put that over here. Q squared times a 1 over x squared. Okay? So that means we have to solve this differential equation. In my notes, I saved myself some time and some stress by calling this sucker A. So this is A over x squared. And the differential equation that we want to solve is, no, I divide by m so that you can actually get an A. Let's do that. Let's just divide by m. And we're going to call that A. Equation that we want to solve is dot x equals A over x squared. And at first I was like, I don't want to solve this. Why? It's not easy. It's not separable. Technically at this point it's not separable, but there is a way of making it separable. The solution that, well, the substitution method that I used was, well, and again, I'm not going to lie, I didn't know how to solve it off the break. It took me to go back in my notes and actually look up a sufficient substitution, and I felt that this was the best way of going about it. I say I'm going to make the substitution that u is equivalent to x dot. So why am I doing that? First of all, I can get rid of this. Why am I doing this substitution? Well, because the whole purpose of this is to make it separable. In this case, with respect to x. So I say u equals x dot. Therefore, du dx is dx. No. So du dt is x double dot, which is d dx of du dt. No. No. ddx of dx dt of dx dt. Right? Right? Chain rule? Yeah, it's chain rule, because this is, those two will cancel, and then you have ddt of dx dt, and that is that. And dx dt, what is that? This is u. So this is du dx of u dotted with dx dt. And yeah, sometimes you have to do that again. This is also sufficient for you to say ddt of 1/2 x dot squared. Because what is this? this is 2x dot x double dot. So if you multiply this times an x dot, if you multiply both sides by an x dot, then you can have this relationship, and then you integrate and you separate and get rid of a lot of shit. But I figured that this substitution with du dt was a lot better. It's a little bit easier. But this is also another method of going about it. This method is more related to like a kinetic energy sort of method of solving this differential equation. It works because you already have an x double dot here, which is an acceleration. Then you just need an x dot, and then make this function look like this function, and then get rid of the dt's. But anyway, let me go about through my my logic by using the u substitution. So I have u dot equal to d dx of u times u dot. Get rid of this. And let's not forget, u dot is u double dot. So we have u dot equals d dx of u times not u dot, but just regular u, since dx dt is u, and this has to be equivalent to a over x squared. Bada bing, bada boom. We don't have to worry about this anymore. Why? Because this is separable with respect to u and x. This is exactly what we wanted. One more erase mark. I'm sorry. I'm not looking at my notes, so you can see that I'm doing this somewhat off the fly. My notes more or less say the same thing, but you have u dot, which is u x double dot, is equivalent to a over x squared, and a over x squared is equal to u du dx. Dx on this side, a dx over x squared, is equivalent to u du. We have a separable ordinary differential. This is minus a over x plus a constant c. It's an arbitrary constant at this point until we apply not boundary conditions, but initial value conditions. Not initial value boundary conditions, because this is a position. Initial value boundary conditions. Natural log of u. Hold up. Problem. U du, not natural log of u. This shiggity is. Oh, I think I made a mistake. Robert made a mistake. Robert made a mistake. Robert made a mistake. This is u squared. Actually, maybe not. So this is u squared. U squared, square root, is minus a over x plus c equals the velocity. And so we need a position. We need to do a separate integral. Dx dt is square root of minus a over x plus c. Actually, what we may want to do is move this over. So I'll do that in just a minute. separable. So you have dx over root minus a over x plus c. Yeah, I made a mistake in my notes. dt. Oh, yep, just had to crack my back a bit. So what is this? What the hell is this? Lordy. This is something where you might have to look up the integral. In this case, let's see. Yeah, if x was up here, you'd be okay. X isn't, so you're not exactly all right. I will probably do this in the next video because I'm going to have to look up what this actual integral is. Better yet, can do. Let's look up the integral. Give me 1 minute. Let's look up the integral. Yeah, let's look at the integral. Because the mistake that I made was in my notes was I said it was separable, but then I said that u times du was natural log of u, and that's not true. That ain't true. U du is not natural log of u. Lovely, Robert, lovely. Actually, and then there's a 1/2 here, isn't there? Yep, there's a 1/2. So then you got an extra 2 factor, which isn't really going to help us, but that's okay. Of root 1 over x. Actually, do we have to do that? Yeah, that's a good question. Do we have to do that? And I ask, this is a kinetic energy, right? This is a kinetic energy term, and I'm saying that the kinetic energy is proportional to a position. We released it from. Okay, I think we can do this. We can do this without solving this equation here. Yeah, we can do it without solving this equation here. And I had to, again, you got to stop. Sometimes you got to stop them. So already, this is how I solve problems, and this is how you go about thinking about certain things. Let's look at the initial conditions. This is exactly what we wanted anyway. So let's not do too much work. We're releasing it from some position D in phase space D with 0 velocity. This is 0 not. These are your initial conditions. So at x equals d minus a over d plus c equals 0. Therefore c equals a over d. Cool. Cool. We've got the velocity over 2 equals minus a over x plus a over d. And at the limit that x goes to infinity, you get x dot over 2 is equivalent to, this is 0, a over d, or, alright, so let me, first and foremost, let's organize this just a bit better than I have been. So our phase space initial condition was d0. Our equation is u squared over 2 is equal to minus a over x plus c. Okay. We found that after applying this condition, c, our arbitrary constant, is now a over d. So u squared. If you notice, I erase a lot more when I haven't exactly planned out the problem. And that's what I get for, I had in my notes I had this exponential function, and then I'm like, it's not a natural log, plus a over d. Take the limit as x goes to 0, as x goes to infinity. This is sort of like, this is your critical, this isn't critical velocity because critical velocity is when time goes to infinity, then we'd have to do an extra integral. But limit of u squared over 2 equals a over d. Therefore, what is the velocity? It is root 2a over d. And where a was q squared over 4 pi epsilon naught. And there's your solution. There you go. So that's going to be the end of chapter 2. Next time we go through this, we're going to do chapter 3. I'm going to do chapter 3. Probably no more than like 5 problems. And we'll be moving on. Moving on up. Oh yeah, videos on thermal. Thermal videos, I'm going to get a few of those up maybe later today. Well, no. Tomorrow won't be. Tomorrow I'm going to be on a train for 32 hours. Yeah, I go back to Fargo tomorrow. So we'll see what happens. Probably upload a video on Sunday, Monday. Well, Monday evening because I have work Monday morning. Alright guys. See ya. Bye-bye. Stay pimpin'.